Welcome to Spring LIB.
All right, a question regarding length contraction and time dilation under special relativity. And so the question asks you to compare classical time and classical length with relativistic time and relativistic length. Right. So first part is about length contraction, and you're going to use equation 26-3a for that. And this states that L equals L naught times square root of 1 minus v squared over c squared. Yep. And so you could rearrange and square the terms. So divide by L naught, divide both sides by L naught, and then square both sides. You get L over L naught squared equals 1 minus v squared over c squared. So remember, velocity is what we want here. And how we get L and L naught, I'll get to it in a second. But let's make all of this in terms of v. So what you get is v equals, so move the v squared over c squared to the left-hand side, and the L over L naught whole squared to the right-hand side, and then make v the subject and take the square root of that. What you get is v equals c times 1 minus L over L naught squared. Okay. And so when we're looking for difference in the relativistic and between the relativistic and classical lengths of 1% length difference, that means that your relativistic length, L in this case, remember length is shorter under special relativity, so relativistic length will be less than your rest length. Okay, and so what this implies is that v equals c times 1 minus, so remember we want 1% difference, right? So here, so L over L naught will actually be, L naught will be bigger, so L will be 0.99, where L naught will be 1. So this is 100%, this is 99%, so that's a 1% difference, right? So L over L naught squared is just 0.99 squared. 0.99 quantity squared. And that gives you 0.141 times the speed of light. Okay. Then part B is about time dilation. And here we use the time dilation formula given by equation 26-1a. And that states that delta T naught is equal to delta T, rest frame and moving frame, times 1 minus v squared over c squared. Again, you do the same stuff with the rearranging as we did here. And so let me write that down. Rearrange. What you get is that v equals, in pretty much the same way, c times 1 minus delta T naught over delta T whole squared, because as we see here, delta T naught is on the left-hand side, and here L, the moving length, is on the left-hand side. So now, we do something similar. We find something similar to here, where we're talking about the length difference. Now with time, a 1% difference in time difference means that, remember, moving clocks are slower, have measure longer times than measure shorter times than clocks at rest. So 1% length difference had length less than rest length, but in this case 1% time difference will have relativistic time greater than classical time, or rest time. Let's call it rest just for consistency. And so what that gives us is that delta t naught over delta t will in this case be 1 over 1.01 because, sorry, delta t, because the rest time, because moving clock runs slower, measuring longer time than rest time, right? This means that v, in this case, is c times 1 minus 1 over 1.01, 1% change, all squared, and that gives you something very close to 0.140 times the speed. And that's it.